So yesterday we showed about Reynolds decomposition, and towards the end of one of the sessions somebody asked that what happens for compressible fluids. So that's what we are going to talk about, another decomposition which is called Febvre decomposition, and how Febvre decomposition and Reynolds decomposition interact with each other, what are the interrelations between them. And we'll also go into not only on Reynolds average linear stress simulation, but also the concept of large eddy simulation in this lecture. So, as I mentioned, if you have a random turbulent signal, one can actually break it down in terms of a mean quantity and a fluctuating quantity. We discussed that yesterday. This is called the mean component, fluctuating component, and this decomposition is the Reynolds decomposition. In the case of compressible flow, where density changes significantly, then the same quantity Q is split like this. This is called Febvre mean. As you can see, this is shown with a tilde. Over bar essentially refers to Reynolds averaging procedure. So it's a density weighted averaging process, and whatever is left here is essentially a Febvre fluctuation. So this one is called Febvre mean. Whatever is left is Febvre fluctuation. Okay? The reason behind it, I'll explain. Now, where it is used for high-speed compressible flows, so if you are talking about flows above Mach number 0.3, you will need this kind of decomposition. Even for Mach number less than 0.3, if you are dealing with reacting flows, where because of chemical reaction, because of the thermal expansion effects, your density changes by 7-8 fold, you can't afford to keep incompressible formulation. You have to account for density change, and that's where this decomposition is used. Clear? Now, let's go into the properties of Febvre decomposition. So, Q tilde is defined as this quantity, right? Now, if I actually write Q as Q tilde plus double prime, you will get this expression. If I compare the left hand side and right hand side, you can appreciate this will cancel out, that means this quantity. See? Happy with that? Means Febvre fluctuation multiplied with density. When you take Reynolds average of that goes to 0. If I actually now break this density into a mean density and density fluctuation, and if I actually expand this, essentially I'm just taking product of that and then Reynolds averaging and addition operation. It's a linear operator, so they commute. So in that case, if you just take average of that, so you will see this remains, this one goes to 0 because Q prime bar is 0 by definition. It's a fluctuation, mean of fluctuation is 0. This one again is 0. Here, because mean of density fluctuation goes to 0. This one remains. So, this is the interrelation between the Febvre mean and Reynolds average quantity. So, essentially, within Febvre mean, this correlation is already included. Clear? That also essentially tells you this is Febvre mean is not equal equal to Reynolds average. Clear? Obviously, how far they are, that depends on this quantity. But you can also appreciate when there is no density fluctuation, these two are going to be exactly equal to each other. So, in the region of the flow where density does not change, Febvre mean reduces to Reynolds average quantity. Now, Q double prime Febvre fluctuation is defined by Q minus Febvre mean value, as we discussed. So, if I now put this in, this is the expression for Febvre fluctuation. Clear? Happy with that? What I have done, nothing new. In the place of Q tilde, I have put that expression. And then Q minus Q bar is nothing but Reynolds fluctuation of Q. Clear? If I now take average of that, this bit, you can see this one goes to 0, but the second term is not necessarily equal to 0. Clear? So, in the case of Reynolds decomposition, mean of the fluctuation was 0. In other words, what I'm telling you, this quantity is 0. Mean of the fluctuation was 0. In the case of Febvre decomposition, mean of Febvre fluctuation is not equal to 0. It becomes 0 once you density weight. Clear? So, it's very, very important to actually understand that as apple is not orange, Reynolds mean is also not Febvre mean. That poses difficulty for from the point of view of computational simulations, because when we are actually running simulations for compressible flow, we solve for Febvre mean quantities, get Febvre fluctuations perhaps from that, but experimentalists don't generally measure those quantities. They measure Reynolds average, Reynolds fluctuations, because it is easier to measure those things. Think about how you actually measure the Reynolds average or fluctuations. You are essentially time average or time integrated, or you are essentially doing ensemble averaging in the statistical homogeneous direction. That's relatively easy to do experimentally. Density weighting means you have to actually measure density, then multiply it. It's much more complicated operation from the experimentalist point of view. That effectively means that when you are dealing with compressible flow, comparing the simulation results with experiment poses additional challenges, because experimentalists are reporting something which you do not see, and they don't generally measure what computational scientists are coming up with. Okay? So keep that in mind. Properties of this. So if I write this quantity, Reynolds mean of Febvre average, this is defined as this. Here. Now rho bar is already averaged. So it's like a constant quantity. So when we average it, it comes out of the average. This is already averaged, right? So effectively, if I actually average a series of constant numbers, essentially we'll get the same number, right? And that's why I will get this. But please understand what I'm talking about in the context of Reynolds average Navier-Stokes simulations. Okay? not necessarily for large acceleration so far. This, see what we can get by definition, that's this quantity, by definition of the Fabry averaging process is a density weighted averaging, right? Clear? This is already average, we have already shown that. So essentially if I write it like this, I'll get this. Clear? Does it make sense? For constant density flows, as I told you, Fabry boils down to Reynolds average. Properties, taking derivative and mean of that and derivative of the mean, they commute from the Reynolds averaging perspective. It commutes with respect to space as well as time. If I do this, essentially boils down to this, because average of average is exactly the same. Clear? By the same token, this essentially means is del x of mean of Fabry mean, which we already showed that that's going to be the same as this one. Clear? This, which is basically Fabry mean of this quantity, that is given by this, that is not necessarily equal to this one. Okay? So, Fabry mean of a gradient is not the gradient of a Fabry mean. Clear? So, Fabry averaging does not commute when you are dealing with any kind of derivative operations. Does it make sense? Why? Obviously, you can see that if I use chain rule, I'll have one of these terms, but there will be an extra term as well. And that is not necessarily equal to 0. Which essentially tells this, what I already mentioned. Now, why does one need Fabry decomposition? Let's see. This is our mass conservation equation. Yesterday we derived that, right? If you deal with constant density flows, this term goes to 0, isn't it? Rho is a constant, it comes out of this derivative and it boils down to this, which is nothing but divergence of velocity is equal to 0. And very often people actually talk about this as continuity equation, but they often don't mention the intermediate step in between. Actually, this quantity which you are looking at, it basically represents something which is fractional change in fluid volume with respect to time. It has a name, it's called dilatation rate. What it is trying to tell, mass is density times volume, right? If density does not change, does volume change for conservation of mass? So if density doesn't change, volume does not change. It's basically telling that fractional change of volume with respect to time is equal to 0 for incompressible fluid. So hopefully you can follow the discussion that this is not going to be 0 for compressible. Now, let's say my density is changing, dealing with compressible flow. Let me break down all these instantaneous quantities rho as rho bar plus rho prime. That's the Reynolds decomposition, mean value and the fluctuating value. Similarly, Ui will be broken down to Ui bar plus Ui prime, Reynolds mean and the fluctuation. Fine? And then this equation boils down to this equation. A little bit algebra is done in between, but nothing else, conceptually nothing different. At this point, let me Reynolds average this equation. Let's look at things one at a time. If I take average of this quantity, I have already told Reynolds averaging and differentiation from units. So that means if I take a over bar here, essentially I have to consider over bar of this quantity. Isn't it? So that effectively gives me this part which is written within the bracket. Clear? You can appreciate that this one, mean of mean, is basically going to return you this quantity. Mean of this is going to be 0. Happy with that? If I now take an over bar on top of this one, effectively that's essentially del xi of over bar of this. So that will give me over bar on top of this one, over bar on top of this one, over bar on top of this one, over bar on top of this one. Clear? These are already mean quantities. Averaging of that will give this. Happy? This is already a mean quantity, so it actually acts as a constant. It comes out of the averaging process. That's what happened. But then you have Ui prime bar. What happens to that? By definition, it's 0, right? It's a mean of fluctuation. Similarly, look at this one. This is already mean. So it acts almost as a constant. So it comes out of the averaging process. Then you are left with rho prime bar. What happens to that? Goes to 0. This one is like that. Okay? The equation now boils down to this. Now, where is the problem? Yesterday, I told that in the Reynolds average Newcastle simulations, you solve for the mean. Yes? So when you actually get the solution, you get all the mean values like mean velocity, mean temperature, so on and so forth. And I also showed in order to do that, effectively you get more variables than the number of equations that you have at your disposal. And that's why you need models, right? Now I have introduced something which is very problematic. This is an unclosed term. And that unclosed term, most importantly, is sitting in my mass conservation equation, which originates because of the correlation between density fluctuation and velocity fluctuation. Why it is problematic? If I cannot approximate it properly, I can't guarantee that my mass conservation is going to be maintained. That's a very, very strange situation. You have a pipe on this side at the inflow, some mass flow rate you are getting. If your model is not correct, at the outflow you are going to, under steady state, you are going to see a different mass flow rate. It's completely unphysical, completely unacceptable. Clear? Although mathematically this equation is correct, if you implement it from the simulation perspective, it's a recipe for disaster. Because I don't think any of you will be happy as you are going to apply some mass flow rate and something else is coming out from the other side of your domain, even under steady state. So, let's see what one can do now with respect to fabric decomposition. The the same equation. Now, we are going back to mass conservation equation once again. Rho remains as it is. I am breaking Ui as Ui tilde plus Ui double prime. And that gives me this term. Happy with that? If I average now, Reynolds average, so if I Reynolds average over this term, essentially time derivative will come out, we will have rho bar. Okay? If I take Reynolds average over this term, essentially del xi will come out because the derivative and the averaging commute, and you will have over bar on top of that. Ui tilde is already average, so it is going to come out of the averaging process. You will have rho bar Ui tilde, and you will have over bar on top of it, but by definition, I showed earlier that density weighted Febvre fluctuation is 0. So this one goes to 0. You will end up with this. That is much better looking equation, but this one defines. So effectively, the whole equation is Reynolds average. I'm telling if I am writing in terms of Febvre average. So it's the operation is Reynolds average. Okay? If the wording essentially is confusing to you, I'll change it when I send it to you. But effectively, we are Reynolds averaging the whole equation, but we are writing it in terms of Febvre average. Clear? I guess that's what you are referring to, right? Fine, I'll clarify it for you. Couple of things to note. If I am solving for Febvre averaged velocities, and if I am getting mean density, this equation is absolutely fine. Okay? So that's what we do from the point of view of compressible flow, or in the case of reactive flow. Solve for essentially mean density, Febvre average velocities, Febvre average temperature, Febvre average mass fractions. Clear? In that case, at least mass conservation equation does not have any kind of approximations. Obviously, momentum conservation equation will depend on the model. Scalar equation will depend on the model. Energy equation will depend on the model. But at least mass will be conserved, which is a better state than this one. Clear? So hopefully you can appreciate the motivation behind Febvre averaging, why Febvre averaging is used instead of Reynolds averaging. Okay. Now, this has implications. Previously, turbulent kinetic energy was just Ui prime over bar divided by 2. That's what we showed yesterday, right? But when you are talking in terms of compressible flow, we are not going to talk about K, we are going to talk about K tilde, which is essentially Febvre mean kinetic energy. It's defined like this. It's not quite this, but it's almost like that. I'll explain later on when we are going to go through the tutorial question. Come back to that. But if you actually derive a transport equation for this quantity, you will have all of these terms. This is transient term, as you know, mean advection term or contribution term. This one, yesterday we called turbulent kinetic energy generation term for contribution due to the mean velocity gradient. Yesterday, this term was not there at all. Why? Think about incompressible flow. If in the case of incompressible flow, this double prime will become single prime. Mean of fluctuation becomes what? 0. So this term essentially completely disappears in the case of incompressible flow, but it is an important term for compressible flow. This one is called pressure dilatation term. This is originating because of pressure fluctuation as well as the divergence of velocity, but divergence of velocity fluctuation. I told the divergence of velocity is called dilatation rate, and that's why it's called pressure dilatation term. If you consider this to be only one prime, that means Reynolds fluctuation. For incompressible flow, this term disappears because divergence of fluctuating component of velocity is 0 for the incompressible. This part involves both molecular diffusion of kinetic energy as well as molecular dissipation of kinetic energy. So the dissipation rate term actually is hidden here. This part is the pressure transport term, this is the angular transport term. Okay? So you can see immediately at least these two terms are extra terms which are coming into the equation because of the compressible effects. And it is extremely important to actually know these things, because in commercial codes, very often the standard incompressible flow turbulent kinetic energy equation is coded. If you are using it for compressible flow, you have to actually implement these extra terms. Obviously, these are effectively unclosed terms. You need models for this. And actually, they are quite important terms. You can't ignore them. In addition to that, there will be extra terms coming here, which is not there. If you expand it, there will be some extra terms which are not there for incompressible. So you can see the comparison. Now, if we look at the T4 term, which I told is the combined effect of molecular diffusion term and the dissipation of rate of kinetic energy term. In the case of Newtonian incompressible fluids, it's this form. In the case of compressible Newtonian fluid, you have this term, which is corresponding to this one. This is the dissipation rate. But here, it's a Febvre mean dissipation rate defined in this manner. Okay? This is corresponding to this one. And then you have an extra term sitting here. Again, this extra term goes away in the case of incompressible flow, because look at this. Here you have a fluctuating component of UK. For a moment, mentally consider as if instead of having the two double primes, you have single prime. Okay? If you take derivative of that, you will get essentially exactly, that is a del UK dashed del xk, which is divergence of velocity fluctuating velocity component, which is 0 in the context of Reynolds decomposition. Similarly, you have this one sitting there. If you think instead of Febvre fluctuation, Reynolds fluctuation is going to be 0 again for incompressible. So this term completely vanishes for incompressible flow, but it's very much there in the case of compressible flow. So, fortunately, all the flows that I have seen so far, this term is actually quite small in comparison to this. So, although a model is needed, but modeling of this term does not play a major role. But that doesn't mean anything. Obviously, I'm telling from my experience, and I have not seen every possible flow. Nobody can. So essentially, T2, which is the mean pressure gradient term, once again, pressure dilatation term, T3, and TV, which is basically a viscous contribution coming because of the divergence of the thread fluctuation velocity. All of those terms will play variable density flows, so compressible flows or turbulent reactive flows as well. Clear? The implication? Before I move to LES filtering now, so now we are changing course. So far we have been talking in terms of RAL simulation. Now we are going into LES. But before we go there, I just want to emphasize that I just mentioned about turbulent magnetic energy transport equation in the context of RALs, and I told there are extra terms appearing because of the variable density effects. Dissipation rate transport equation, exactly. Equation of dissipation rate transport I did not show. This is a really messy equation. But if you consider the first tutorial problem that we did yesterday, you can follow the same procedure and come up with a transport equation for dissipation rate. And you will find there are quite a number of extra terms because of density variation in the dissipation rate transport equation. So the conventional dissipation rate transport equation, which you will get in any commercial course like Fluent, StarCD, CFX, they are going to be valid for the compressible flow. But if you're doing for compressible flow, you need to actually bring in the models for those extra terms. And the models for those extra terms are not widely validated. So keep that in mind. Okay. So LES filtering process. In LES, first important thing to remember that you do not, when you are actually running LES, you do not actually bother about it, this operation, because you already get this one of the simulation. But conceptually, what it is, it's a convolution operation. G is essentially the filter kernel, and you actually do this kind of integral operation to get the filter kernel. Clear? This is essentially the filtered value. Here is the filter kernel with this realizability thing. So if you integrate it over R, GR will integral GR dr is going to give you. Okay? It might seem a little bit different because all the things that we talked about in the case of Reynolds averaging will no longer be directly valid anymore. Filtered value of filtered quantity is not equal to the filtered quantity. Why? Put it in this equation, you will immediately understand. Okay? So effectively, you are getting this, and on top of that, if you put another one, it's not going to give you the same thing. Okay? Because you are actually spatially shifting it by distance. At least conceptually, does it make sense? Similarly, this, as this one is not equal to this is not 0. Okay? Similarly, this is also the case. In this case, when I'm talking about tilde, essentially the definition is exactly the same, but interpret over bar as the filtering operation rather than Reynolds averaging operation. Clear? Or in general, filtering and differentiation, they don't commute unless this one, GR, is a homogeneous filter. That means it doesn't have any reductional property. Only then this will commute. These are the different filters which are considered. Once again, I'm telling when you are running LES, you don't care about it. Sometimes you actually use the filtering as a part of some kind of post-processing in order to get some model constant dynamically. Only then you care about filtering in actual LES, but conceptually all the filtering means you are getting filtered quantity effectively means you are essentially making mistakes. Clear? The only filter out of this is Gaussian filter where differentiation and filtering they commute. Okay? These are essentially how they behave. Box filter is basically a state function. Gaussian filter basically is a Gaussian function. No surprises there. Okay. Sharp spectral filter is actually given in terms of the sine function. It is in the wave number space, it is going to look like a box filter. But when you are looking at in the physical space, the problem is that it has undershoots and overshoots. Okay. It may not be a major problem for velocity because velocity in principle can go from -infinity to +infinity. But if you are thinking in terms of, say, mass fraction of a species, that's bound between 0 and 1, right? You cannot have a negative mass fraction, which is meaningless. This one can give rise to that kind of unphysical things. Nobody really, although it's mathematically possible, nobody really uses sharp spectral filter. At least in this original form, most of the time people are using Gaussian filter. Because it offers extra advantage, as I said, it's especially invariant. It does not create any problem in terms of commuting derivative and the filtered value. Clear? So if you are ever commuting filtering and differentiation in the context of LES, please keep in mind that implicitly you are accounting for a spatially invariant filter like Gaussian. Clear? Effect. These are essentially the effect of filtering. I have taken one of my direct numerical simulation cases. It's a premix flame. Red part is the burned gas, blue part is the unburned gas. Okay? It's propagating in this direction. It's a direct numerical simulation data. What direct numerical simulation is, we are going to talk in the second lecture today. But effectively, all the length scales and time scales of turbulence that we discussed yesterday are properly resolved without any kind of physical approximation. So you can actually consider that data as if it's an experimental data with the kind of resolution which is hard to get in experiments. Now, I have explicitly filtered that with different size filters, and the filter size increases. Okay? Because of the convolution operation, you can see this image gets increasingly smudged. Isn't it? For example, this island that you can see this one for a medium size filter is completely gone there. Here I had a little bit of wrinkle. That wrinkle starts to march. Here it has already marched. If you look at the extent of wrinkling that you can see, that is decreasing in this direction, isn't it? If I go for even larger filter, because it's a statistically planar plane, ultimately you will actually get a flat line. That is in the limit of when the LES goes towards RAS. Okay? So I'm giving you a hint that when filter size is very large, LES tends towards RAS. Okay? Obviously, the physics doesn't go away. The part which we are not resolving, that means the information that we are losing because of filtering, that is taking place at the sub-grid level. And that physics we have to actually account for in terms of models. Once again, models mean glorious name for approximation. Okay? So, for example, in actuality, the grid size is bigger for LES in comparison to DNS. So in other words, I'm telling that as I am increasing my filter width, the grid sizes are becoming bigger. You can see this is the velocity field in a 2D plane. You are seeing that. If you have DNS level of resolution, you see much more detailed fine structures. So degrees of freedom of grid size increases in that direction. Clear? What filtering does, I told it's already smudges things, it smoothens things, right? Filtering operation is not only unique to fluid mechanics. People use filtering operation as a bandpass filter for signal processing all the time. And there are filtering operations in MATLAB. If you have MATLAB, you can play with it. But this is an instantaneous signal. And if you actually filter it, it smoothens it. This is the effect of filtering. Okay? As the filter size goes towards 0, you will actually capture the instantaneous behavior. So when the filter size is really, really small, you are approaching towards the DNS limit, direct numerical simulation limit, where you are resolving everything. And when you are going for very large filter width, I have written mathematically delta filter width goes to infinity, obviously. That's a mathematical way of talking. Nobody really uses infinite filter size, but effectively what I'm telling, that when filter size is very large, you go towards RAS. Clear? So, this was our momentum conservation equation in the absence of any particles. That's the instantaneous one. Okay? If I filter this equation, it will take this one. If I consider a spatially and temporally invariant filter, if you have issues to understand that, let us go back when I am talking about this one. See, when I am expressing this one, it is not dependent on time, and it is only dependent upon R, isn't it? Clear? So it's a spatially invariant as well. Every x, y, z location, the shape of the filter does not change. Happy with that? This is essentially an example of spatially and temporally invariant. So if I assume my filter is that kind, then my equation will look something like this. Happy up to this point? Now, from the definition of Febvre filtering now, this quantity, I can write it rho bar ui tilde. Clear? By definition, rho ui bar is nothing but rho bar ui tilde, density weighting. This quantity, however, is unknown to me, because when I'm solving for Febvre filtered quantities. So what I have done, I have actually added an extra term like this in the equation. And if you look carefully, here I have negative sign, here I have negative sign. Two negative signs will make it positive. The second term will be exactly identical to this term. So I have added the same term, left hand side and right hand side. Okay? This term is identical to this one, this term is identical to this one. And this essentially is our unclosed term. And this quantity is our subgrid stress. This is the unclosed term we need to model in order to solve filtered momentum equation. Clear? Before I leave this slide, exactly the same term essentially appeared as Reynolds flux term in the RANS. Okay? If you do a little bit of algebra, and if you do this, it will come out to be rho u prime, ui double prime, uj double prime bar in the case of RANS. Okay? In the same manner, if I consider a species conservation equation, filter it, I'll get this expression. If I consider spatially and temporally invariant filter, then derivative and filtering will commute, then I'll get this, and using the same trick, I will get this equation, but this one is going to be my unclosed term, which is subgrid scalar flux. Yesterday, in the context of RANS, we got the same thing as rho u prime y prime. In the context of Reynolds, the Febvre averaging, it will come out to be, in the case of RANS, rho u I double prime y alpha double prime. Exactly here. Okay? But it's unclosed, whether it is RANS or LES, you need modeling. Here? By Febvre averaging or Febvre filtering, I have ensured my mass conservation equation doesn't need any modeling, but I still need models for momentum conservation and species conservation. And same thing appears in the case of energy equation in terms of subgrid flux or temperature or enthalpy, how you express your energy equation. Okay? So we talked about fundamental concepts of Reynolds and Febvre decomposition. Hopefully, some of the things that we discussed yesterday will start to make a little bit more sense based on this information. So we'll stop at this point. We have talked about the principles of LES filtering and its properties and the relations between LES filters and Reynolds mean values. So in the second lecture, we'll focus. So we have talked about RANS, we talked about LES, talked about DNS. Now we are going to actually see what these three different simulation methodologies entail and what the challenges are in the second lecture.